This is lecture 9 of Machine Learning and Bayesian Inference. In the last lecture, I finished off by starting to talk about how you might meaningfully establish that one classifier is better than another. And in order to do that, we have to get into the realms of statistical testing. And I'd just got as far as giving an example but based on essentially the simplest form of statistical testing that you could think of. And the outcome there was that because we are essentially estimating an actual probability of error by counting the number of errors in a test set of size n and then dividing by n, the central limit theorem comes into play, and we can work out a probabilistic bound that tells us that with some specified probability, and we generally use 0.95, the actual probability of error, which is a mean, falls within a particular bound around our estimated or our measured value. But we need to go a little bit further than that. And before I go further, I just want to point out that there is a reason to be a little bit careful in dealing with these arguments. To remember that our estimate is actually a measured average. We're summing up n things and dividing by n. As a result, its variance is not quite as straightforward as you might hope. If you forget that, then you end up doing something that's not quite right. So let me just expand on that a little bit. The mean of the underlying random variable that we're dealing with is mu, and the variance is sigma squared. Okay, nothing has changed there. But we can also ask about the mean and the variance of our estimate x hat sub n, which is the thing that we're really interested in. Now, it's easy enough to work out what its mean is. The expected value of x hat sub n is just the expected value of this measured average, and because expectation is linear, we can bring the expectation operator through the sum, and the expected value of the ith measurement, because we're just measuring the random variable x, is mu, so we count that n times in the sum and divide by n, and we just end up with mu. Okay, so everyone's hopefully happy about that. It's left as an exercise, so this is something for supervisions, to show that the variance of x hat sub n isn't sigma squared, it's sigma squared over n. Okay, so the variance gets better the more measurements you take, which is what we would hope for. And I've already used that in some of the preceding slides. The reason you might want to be a little bit careful to remember that is that if you just treat x hat sub n incorrectly as a single random variable rather than a measured average here, you end up with something slightly different. Now, all that's happening on this slide is that I'm taking just an individual random variable y with a known mean and variance. Okay, we can normalize it easily enough to have a mean of 0, and it's a fairly straightforward exercise again to show that if you divide a random variable by its standard deviation, okay, sigma, not its variance sigma squared, then you change its variance then to be 1. Okay, so this is the important message. The random variable that you then renormalize by subtracting its mean and dividing by its standard deviation has a mean of 0 and a variance 1. Now we can still apply the same arguments as before, in terms of then finding a band that puts the random variable within some known interval around its actual mean. But that's a slightly different result to the one that we were talking about recently, because the variance of y appears in there rather than the variance that corresponds to the measured average that we were using earlier. Okay, so you do need to be a little bit careful. The manipulations are practically identical, but you need to be keeping track of whether you're dealing with a single random variable or a sum of them. So, where do we go now? Well, once again, what we're actually interested in is comparing two classifiers. So what I really want to know is not just that with high probability my estimated error for a single classifier h lies within a particular bound. I want to know whether the difference between one classifier and another is of significance to me. Okay, so everything I've said so far, in particular, for example, in this example here, I had a single classifier h, and I'm estimating its generalization performance. And what I'm learning is that the actual generalization performance for that classifier h is within some kind of bound around the estimate that I've made. But I actually want to know not just about the actual performance of a single h, I want to know about the difference in generalization error between two classifiers h1 and h2. So this is the quantity that I'm actually more interested in. But this fits perfectly happily into the framework that we already have. Okay, I can just estimate that difference, d hat, by estimating the error of the first classifier h1 and estimating the error of the second classifier h2 on a couple of independent test sets. And then because the estimate itself that we're making, okay, because d hat is then still a sum of random variables, okay, it's the difference between this guy, which is a sum of random variables, and this guy, which is a sum of random variables, so it can still itself be expressed as a sum of random variables. The central limit theorem still applies. And it's entirely trivial just to show that the estimate that we're making, d hat, is unbiased, meaning its own expected value is d, which is the value that we're trying to estimate. And as a result of this, we can just carry through the same argument as before. Okay? The two parts of the estimate for h1 and the estimate for h2, are each sums of random variables. The variance of the estimate is the sum of the variances of the individual estimates. Adding things that are Gaussian distributed together gives us something else that's Gaussian distributed. And so the confidence interval for the estimate of the difference in generalization performance between these two classifiers falls out exactly as before. The estimate of the difference is Gaussian distributed around a mean of d, which is the actual difference, and we know what its variance is because it's the sum of the variances of the two estimates. And so in the boxed expression here, all we have in here is the estimate of the variance for d hat, okay, which is has two components which are calculated in exactly the same way as we calculated or estimated the variance for a single estimate of generalization error for one classifier H. Okay, this part of the expression is exactly as it was before. Now, M1 and M2 are the size of the two independent test sets, S1 and S2. But in practice, it's common just to use the same test set to make both of those estimates. Okay, not strictly defensible, mathematically speaking, but generally good enough for what we're trying to achieve. Now that still doesn't tell us quite what we want to know. What we've got now is a probability, as usual 0.95, that our estimate of the difference between the generalization performance of H1 and H2 is within a certain bound of its actual value. Okay, that's not quite what we want to know for the following reason. We're actually interested in whether one of those hypotheses, H1, is better than H2 or not. Okay, so what we actually want to know is whether the difference is bigger than 0. Okay, we want to know if one thing is actually better than the other or not. So, we are measuring this random variable d hat, and we'll get a particular value for that measurement when we actually calculate the estimate using a test set. And you can imagine, for instance, the case where there is no difference between these two classifiers H1 and H2. So the actual value of d is 0. Okay. Well, we know that the mean of the estimate is d as well. Okay, we know it's an unbiased estimate. So larger values of that estimate are less likely, even though you're going to get some random variation. One way of thinking about this is that if it's very unlikely that when d is actually 0, a measured value of d hat would be observed, then we can be confident that the actual value of d is greater than 0. Okay? So what we're actually interested in is this quantity here. The probability that our random variable actually exceeds the real value of d plus the value we measured. And that's known as a one-sided bound. Now, as luck would have it, one-sided bounds shouldn't be giving us any cause for concern, because if we know what the relevant numbers are for a two-sided bound, which is the kind that we've been talking about all along, because we've been looking at expressions like this. Okay, we've been making 1 minus epsilon equal to 0.95, and then looking in some tables or elsewhere to find the corresponding value for z, which is related to epsilon. What we're now talking about is a one-sided bound that looks like this. Okay, so we've just thrown away one of the inequalities. And because the normal distribution is nice and symmetric, we can convert between one possibility and the other very easily indeed. The two-sided possibility is illustrated on the left here. What we're actually talking about is the probability that x falls within the shaded area. If we're only interested in x being bounded above, then we're interested in the shaded area in the graph on the right. Okay, so what that tells us is that the unshaded areas on the left together integrate to epsilon. And the whole density is symmetric, so each of them must have an integral of epsilon over 2. Okay, that's how much probability lives in each of those unshaded areas. So on the right, the shaded area has just grown by epsilon over 2 with respect to the diagram on the left, and we know that our one-sided bound now corresponds to 1 minus epsilon over 2 rather than just 1 minus epsilon. Okay, so one-sided bounds shouldn't be a worry to us. But we're still not quite where we want to be. What we now have is a way of talking about the difference in generalization performance between two classifiers H1 and H2 that we already have. What we really want to be comparing is not a pair of classifiers after training, but a pair of training algorithms. So we want to take into account also the random variation that we might get if we were, for example, to retrain on a new training set of the same size. Okay? So, we need to remember that there's a learning algorithm that takes training data S and maps it to the hypothesis, to the classifier H in each case. And that means that what we really want to know involves this measurement. Okay? Previously, we were talking about this difference, but with H1 and H2 plugged into the actual error probability. Now, this difference depends on the training set, and we're interested in its expected value. So what we're doing here is saying, imagine that I had a training set of size m, but that I could get multiple training sets of size m. Okay? Each learning algorithm, if we train it on a succession of sets of size m, will potentially come out with a slightly different generalization error. There will be some random variation because we're using different training sets, but they're of the same size. Now, what we would really want to do, if we want to demonstrate that one learning algorithm is better than another, would be to show that on average, the difference between algorithm L1 and algorithm L2 in terms of generalization performance is positive or negative, okay, depending on which of the two algorithms we're trying to show is the better. So that's the expression that we have here, summarized by D. Now, unfortunately, of course, in practice, we only ever have one set of training data available, namely S. And we can only estimate the actual generalization errors. Okay, we can only estimate the generalization error of H by doing what we've been doing all along, taking an actual measured average using a test set. We don't have access to the actual quantities, but we do have access to the idea of cross-validation. So, just to recall, in cross-validation we have our training set and we divide it into n folds, each with about m over n examples. We denote by S superscripted with an I in brackets the ith fold, okay, the ith chunk of this data, and by S subscripted minus I the full data set S with the ith fold removed. And then what we were doing previously was estimating performance using the cross-validation estimate, which just says for each of the n folds, take the fold out, use what's left for training, and then with the classifier that you obtain, use the fold that was left out to estimate performance. Using the same idea, we can now estimate D using D hat here. Okay. What we've done is exactly the same thing. We've said we want an estimate of the difference in generalization performance between one training algorithm and another. We actually want an estimate of the expected difference that we'll get between the two of them if we train on a whole bunch of training sets of size m. Now we've just directly carried over the idea of the cross-validation estimate and said that our new estimate D hat is going to do essentially the same thing as cross-validation. Okay, for each of the I folds, we take the fold out. We use what's left to train now both of our training algorithms, and we use the fold itself to estimate performance for both of our training algorithms. And we take the difference, and we now do that and average over our n folds. Now, there is a statistical test that allows us to do exactly the same things with this approach to estimation as we did earlier in considering just individual classifiers rather than algorithms potentially trained on multiple copies of a training set. I'm not going to address the derivation of this in detail, but we get a result that says with probability p, the actual value that we're trying to estimate lives within some specified interval around the value of this estimate based on cross-validation. Now, in this case, we have this value t, depending on both the probability p that we want, typically 0.95, and the value n, the number of folds, which is analogous to ZP in the earlier slides. And this is related to the student's t-distribution, okay, whereas ZP is related to the area under the normal distribution. And now in this case, we have an estimate of standard deviation that appears in our bound, which is computed as described here. And finally, DI is just the part of the estimate that corresponds to the ith fold. Okay, so that, in summary, is the kind of statistical testing that you really need to do if you want to say that your training algorithm is better than everyone else's, or that a training algorithm is better than one or more competitors for the data set that you happen to have available. It is not perfect, but it's a lot more convincing if you do this than if you just say, here's a single measurement of generalization performance calculated for a couple of different algorithms, and one seems to be slightly different to the other. Okay. Now this has been a relatively short lecture, but that's actually a good place to stop, because what I want to do now is go back to talking about learning algorithms, and in particular to start looking at how we might develop a learning algorithm for the supervised learning context that actually tries to give us a Bayesian optimal classifier.